Hello and welcome back to Engineering Key Tutorials. In today's video, we are diving into an exciting problem that explores the principle of fluid mechanics. Have you ever wondered how to determine the density of liquid in a tank using pressure reading? We'll analyze a scenario where two pressure gauges are mounted at different heights on a tank filled with liquid. By applying fundamental concepts such as a hydrostatic pressure and Bernoulli's equation, we'll uncover the density of the liquid step by step. Whether you are an engineer or just starting your journey in fluid mechanics, this video will enhance your understanding and problem solving skills. So grab your calculator and let's go started on this fascinating exploration of pressure and density. So here the problem. We have a tank filled with liquid. Two pressure gauges are attached to the side of the tank. The first gauge is located 6 meters above the bottom of the tank and reads 85 kilopascal. The second gauge is located at 9 meters and read 60.5 kilopascal. Our task to find density of the liquid in kilogram per cubic meter. So in this problem, we can solve it with two approaches. The first approach is hydrostatic pressure formula. And let's start with this approach because it's simpler approach. Let's start with the hydrostatic formula, which is pressure equals rho dH. And here, because we talking about 2 points and the only data we can use to solve due to pressure formula is the difference between 2 points. So we can substitute with delta P equals rho G delta H, which is delta B is the pressure difference and rho is the density of liquid. That's what we are solving for, and G is the acceleration due to gravity, which is approximately 9.81 meter per second squared, and delta H sorry, its height difference between 2 points. First of all, we have to calculate the height difference, which is delta H equals 9 minus 6 equals 3 meters, and pressure difference delta B equals 85 minus 60.5, which is equal to 24.5 kilopascal. And because here we want solve for kilogram, we have to convert the kilopascal to pascal. Then, as you know, the pascal is Newton per meter squared. It's easily in the final convert the Newton to kilogram by dividing by 9.81. To convert the pressure difference to pascal, we have to multiply 24.5 kilopascal multiplied by 1000, which is 24,500 pascal. Let's substitute in the hydrostatic pressure formula. 24,500 pascal equals to rho multiplied by G, which is 9.81, multiplied by 3, which is the height. So the rho, which is the density of liquid, equals to 24,500 pascal divided by 9.81 multiplied by 3, which is approximately equals to 832.48 kilogram per meter cubed. So the right answer is approximately 833 kilogram per meter cubed, which is answer B. Let's move to the second approach, which is more complicated, a little bit complicated, but it's also useful, which is Bernoulli's equation, using Bernoulli's equation. So let's now move to the second approach, which is based on Bernoulli's energy equation. This method is more comprehensive, little bit comprehensive, and considers the energy at 2 points in fluid. And because here we didn't have any movement of the fluid, it's in static state, because here the flow is rested on the floor of the tank. As you know, the Bernoulli's equation has three parameters represent the energy in the flow. The first parameter, which is velocity head, and second one is pressure head and the potential head. Every single parameter of these represent kind or type of energy inside the flow. And here, as we said, because the flow is in rest statement and still stationary, we will ignore the velocity head, and we will consider the two parameters, which is pressure head and potential head at every single point. So let's the solution with Bernoulli's equation approach. So P1 divided by gamma, which is density of the liquid inside the tank, plus V1, which is the potential which presents the potential energy head, which is the height from specific datum. Here we will take the specific datum as the problem said is bottom of the tank, equals to P2 divided by gamma plus V2. P1 and P2 are the pressure at point 1 and pressure at point 2, and Z1 and Z2 are the heights of point 1 and point 2, and gamma the specific weight, which is the weight per unit volume of the liquid, which is rho g. Rho is mass per unit volume multiplied by g, which is acceleration, gravitational acceleration, gives you the weight per unit volume. Let's rearrange the equation. We will get P1 minus P2 equals gamma times Z2 minus Z1. Let's substituting the values that we have. 85 minus 60.5 equals to rho g, which is gamma, multiplied by 9 minus 6. Let's convert pressure difference to Pascal. The pressure difference 24,500 Pascal equals to rho, which is required, multiplied by 9.81, which is the gravitational acceleration, multiplied by 3, which is height difference. Let's solve for density. So density equals to 24,500 Pascal divided by 9.81 multiplied by 3 approximately equals to 832.48, which is also the same answer that we arrived to, which is approximately equals 833 kilogram per meter cubed. So even though we used Bernoulli's equation, we arrived at the same result. Let's make a little bit comparison and conclusion. The both methods give the same answer, and as you saw, the first approach using the hydrostatic pressure formula was much simpler and faster. So I recommend, if you an exam, quiz, something like that, strongly recommended the first one approach. which is easier. The second approach using Bernoulli's equation work too, but it's more complex and better for problems involving in fluid flow, not in static and stationary fluid. In this case, since the fluid is static, strongly recommend the simpler hydrostatic pressure method is better choice. Thank you for watching Engineering Key tutorials. Keep learning, keep practicing, and stay curious.